Hello, Josh. Kindly solve this. We have two problems for today. Number one, simplify this expression.
Okay. So let's start with my solution. So let's just say this solution one. Okay.
Write solution one. So
So one.
they will not understand there are too many numbers.
Sun and one. Okay. So this is the basic of idea of how I got it. So let's say we scale these since these are big numbers, we scale these down. And this is unnecessarily long. So this number can be evaluated by your calculator. When you evaluate it on your calculator, this is what shows up. This number is very clean. Somehow it remained an integer, and it looks similar to the numbers it came from. It has repeating threes and then it ends with a four. It looks very nice. So let's say we scale this down even further, and then we turn it into a very very small number. This will simply become 1156, which is 34. So we see a pattern, we see repeating threes and then a 4. Here we see just a single 3 and a 4. We scale it down. So something is definitely going on. So this one, now that we scale it down, it doesn't look like big numbers, it looks like an algebraic expression. So this square root looks like an algebraic
The
expression. We
idea,
could
can you use, if you can use a different color of pen, so your solution will be more understandable.
So now, what if we make this into an algebraic expression because it looks like one. We let x equals 111. Then 1005 is equal to 999 plus 5, which is equal to, since x is 111, so we can say this is 9x. Oh, plus 6 pala because it's 999 plus 6. Okay. So from this new term we got from 1005, we can simplify this expression into x times 9x plus 6 plus 1. And then we can distribute the x. And then to look this 9x squared plus 6x plus 1 looks similar to x squared plus 6x plus 9, which is a perfect square. This is actually x
So
plus 3
you should have used
squared.
look at your actual solution is blue, right?
Yes,
If you need to explain something, use red.
6x. So we are pretty sure that this expression, this polynomial is also factorable and can be simplified. And in fact, it can be simplified. It's just reversed instead of the constant term having the 3 multiplied to it. It's the variable term. So we can now express this as square root of 3x plus 1 squared, which obviously cancels the square root. This becomes 3x plus 1. I'll just continue the next page. We originally set x is to 1, so we can say that 3x plus 1 is equal to 3 plus 1 equals 3. Hey, so we get the similar number again, repeating threes and then a 4. So what happens if we scale this up not from 1, but to the original problem which has 12 threes? So now let's set. I'll make this a little more formal. This is for this for the real solution. So let's say x equals 1. Then, like earlier, I don't have to show. Maybe I have to show. This 1 0 0 0 0 0 0 0. How many zeros is that? There's another one. Equals 9x plus 6 for the earlier reasons we already discussed. And then we can now express this, the original expression
9x
as
plus 6 because it will become
uh
with an arrow there. You can write use the
wait.
this 9x plus 6.
999 plus
Plus 6,
6.
yes.
So this is our we just turned a very big numbers into a very small algebraic expression. And then like earlier, we get square root of 9x squared plus 6x plus 1, which can again be uh, square rooted. So we get 3x plus 1. And then the 1 can be substituted. X. We get 3x plus 1 equals 3. Oh, it's getting a little hard to write repeating numbers. 3, 3, 3, 3, 3, 3, 3 plus 1.
Plus
So
1.
I have to write again 3, 3, 3, 3,
So your
3,
final,
3,
your final answer
3,
is
3, 3, 3, 3, 4. And again, it follows the pattern like we saw earlier, the repeating 3s and the 4. So this is almost surely our final answer.
okay.
Uh,
So
I think
let me show
it's
our viewers my solutions.
and
So we can exchange page styles. So an alternative solution is my solution. Yes. So what I did is I'll write first the problem again. 12 ones. Times 1 0 plus 1. Okay? So here, I use a different color. So we have noticed that this one is 15 is 3 times 5, correct? And then now I will add 1 0 in between. So 1, sorry, 1, and then I will add 1 0 in between. 105, that's 105. This is 90 plus 15. This will be equal to 90 plus 3 times 5, right? Or times 3 times 5. Or you can also express this one as 3 squared times 10 plus 15. And I scaled it up like I added 2 zeros in between one and the digits 1 and 5. 1005. So this becomes 900 plus 90. So that's 990 plus 15. Correct? So this one, 2 zeros. So this one will become, so this is, I can use powers of 10 here. This will be 3 squared plus times 10 squared. Plus this will be 3 squared times 10 squared. There are 2 zeros in between, so the power of 2 here, the power here, the exponent here will be 2. And this will plus 90, which is 3 squared times 10 plus 15. So next is I scale it up again up to I place 3 zeros in between the digits 1 and 5, and this will be 9,000 plus 900 plus 90 plus 15. So here we have 3 zeros. So using the powers of 10, so we have 3 zeros. This will be 3 squared times 10 to the power of 3 plus, we know that 900 is 3 squared plus 10 to the power of 2 plus 3 squared times 10 plus 15. So we're seeing a pattern. I scaled it up one more time. So this will be, I added 4 zeros to make sure of the pattern. 1, 2, 3, 4, 5. And the digit 5. This will be 90,000 plus 9,000 plus 900 plus 90 plus 15 using the, so we have 4 zeros here. So for my exponent, I will use 4 for the power of 10. So this will become 3 squared times 10 to the power of 4, corresponding to the 4 zeros here, plus 3 squared times 10 to the power of 3 plus 3 squared times 10 to the power of 2 plus 3 squared times 10 to the power of 10 to the power of 1, or times 10 plus 15. Yes. So now we have seen, what we notice here is that we have here a geometric series. Okay, so I'll use the next page. Turn and use blue again. So we notice that we were saying that 15 here is 15 times 1 equals 15. Oh wait, I'll use blue instead, sorry. Fifteen is equal to 15, sorry, 15 times 1 was 15. Now I will insert 0, 1, 0, 1, 0, 5, times 1, and then I will add another 1. And this becomes 1, 1, 1, 5, 5. What's going on in my mind? Just here, look, I will write from our problem, we had this one. 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then 5. 11 zeros. So I was thinking if you correspond this to ones, this is what I was thinking. The, the 12 ones will end up to here. So they correspond. Yes. I was just checking for patterns. My solution was just more of like patterns. So here I would add another 0. So this became 1 0 times 1 1 1, and this will become 1 1 1 5 5 5. We're seeing patterns now. So we can see here we have 3 ones and 3 fives, 2 ones and 2 fives, right? So we have here 3 digits, right? And then we have 3, 2, then we have 2. Okay, so now I will scale it up. So here from our problem, 1 0 0 0 1 2 3 1 2 3 1 2 times 1 1 1 1 1 1 1 1 1 1 1 1. So here we have from here up to here 12 digits, and then from here up to here we also have 12 digits. They correspond, right? So here you will get our answer was supposed to be 12, like here 3 12 3 3 digits here, 3 digits, so three ones and 3 fives. So I will get, my answer is supposed to be 1 1 1 12 ones and 12 fives. 1 2 3 4 5 6 7 8 9 10 11 12. So it's a pattern, right? 12, following the same pattern as we were doing here. So this is the product without using any calculator. This is how you're supposed to get it. So from the original problem, so I will plug this in the original problem. So problem was 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1 times 1, okay, 11 zeros, and then the digit 5. Plus, but this time, wait, I will use a different color for the 1. Let me just erase this one. But this time, we're supposed to add 1 plus 1. So this will become square root of this one plus 1. Okay, 1, 1, 1, 12 1, digit ones, 12 ones, and 12 fives. Yes, so without ever using a calculator, right? I'm able to get the product plus 1. So the, the last digit will become 6, correct? So this will become, I'll try to let it fit here. 1, 1, 1. Okay, remove this one. 1, 1, 1, 12, 1, 1, 1, 1, 1, then 12, 11 fives, 5, 5, 5, 5, 5, 5, 5, 5, 5, and then 5 plus 1, the last digit will turn to 6. So 1 is the square root of this number. Yes. So, but going back to our previous uh, solution here, we noticed that this one is a geometric series, right? So what we can do here is this will become like this. 3 squared times 10 to the 11, right? 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11. And then plus 3 squared times 10 to the 10 plus 3 squared times 10 to the 9th. So I'll use ellipsis plus ta plus 3 squared times 10 squared plus 3 squared times 10. But the last, for our last addend, it will be 15, not just 15, 15 plus 1, right? 15 plus 1 will be 16. Here, this one, the 15, you will add the plus 1. So it will be 16. So this will become, because they're all squared, 3 squared, so if you square them, it will become, this will become, if you convert this, it will become 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, and then the last digit will be 4, right? Square root of this one. So, sorry, let me change the color again back to blue. Squared. So, since it's a perfect square, so my final answer will be 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 4. So let's compare my final answer to that of Joshua's. There, exactly the same. But my approach was more like finding the patterns and then at the end applying the math, right? So Joshua, your takeover that you just passed. So turning to the next page, can you give more
Using the
succinct using the formula for the geometric series?
the solution number 3 is a more rigorous form.
So
So for
you
the
write again the problem just to remind our one, 12 ones, 11 0 and digit 5 plus 1. Yes. Okay. So in the geometric series, what's the in the geometric series what will be the formula? Can you show the our viewers first what will be the formula for the geometric series?
where R is the common ratio and
What do you do with R?
you multiply it successively. You have to here R was multiplied n times through the course of the series until it reach n r to the n. So the number of terms here, so there are n plus 1 terms.
Okay, and then what is the formula for the geometric series? We can
So
just put it somewhere.
the sum is a times r to the n plus 1 minus 1 all over r minus 1, where n plus 1 is the number of terms.
Right there. N plus 1. Okay.
So we can express 111 as 1 plus 1 times 10 plus 1 times 100 plus plus 1 times 10 to the 11. So this is effectively a geometric series. We can identify 1 as A and then R as 10. So we can now turn this into a geometric series. The A will just be 1 and then the R 10 to the number of terms, which is 12 and then minus 1. Then all over whatever R is 10 minus 1. Simplifying 10, 12 minus 1 all over 9. Okay. So for I'm just going to video. For 1 trillion 5, we can simply express this as 1 trillion literally plus 5.
Yes.
So now this big equation is simply just contracted into 10 to the 12 minus 1 over 9 times 10 to the 12 plus 5 plus 1.
Yes.
And then we can impart the 1 and the 10 to the 12 plus 5 all into the 9 on the bottom, and then the fields. Ten 12 minus 1, 10 12 plus 5 plus 9. And then now we can simplify this by first expanding the 10 to the 12 minus 1 and then the 10 to the 12 plus 5. If you're having a hard time with this, just think of 10 to the 12 as a single term. Then we can expand this. Oh, I forgot the square root. As 10 to the 24, and then plus 4 times 10 to the 12 minus 5 plus 9 all over 9. Then I will go to the next page. So we were but I can't think of something else. Maybe we could combine -5 and 9. Still be more contract.
Yes. Start here. Okay. Okay. You remember?
And
This one.
yes.
Somewhere there.
Yes. Again, if we think 10 to the 12 as a unit, then we can simplify this. Let's say u equals 10 to the 12, then we can express this as u squared plus 4u plus 4 over 9. And then u squared plus 4u plus 4 is a perfect square. So we can also make this 9 into 3 squared. And then we can do this u is 2 squared equals square root of Actually, uh, we can remove the squares already. U plus 2
No,
over 3.
yes, you show.
You can cancel this.
No, what will happen? No, no,
You
don't
can.
cancel. Show. By loss of exponent, it will become
What will happen?
u plus 2 over 3, what?
Squared.
Squared, yes. And then square root, yes. Do it step by step for those who are trying to learn.
Then equals 10 to the 12 2 over 3. And then separate them. 10 to the 12 over 3 is almost like 10 divided by 3. You just move it 12 times. So, it just become 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3. 1/3 plus 2/3. These will combine to form 1. So eventually it becomes 3, 3, 3, 3, 3, 3, 3, 3,
Plus 1, sure.
3, 3, 3, plus 1.
Yes.
If only there was a copy paste.
That's okay. Yes, so we got the same answer using the formula for the geometric series. So,
Our next problem.
yes, next problem is find all numbers x such that the mean and the median of the five numbers 2, 4, 2, 16, 6, and x are equal.
Mm-hmm. So
So,
when we look for the median, which is a simple concept,
so
you rearrange
yeah,
all
yeah.
terms
Don't assume that. So for the beauty of the solution,
16, and then you arrange them in the ascending order,
ascending order
and then find whatever is in
or
the
descending
middle.
order.
In if there are even number of if there are even number of terms, you take the mean of the 4 and 6. But when there are odd numbers, there's an odd number of terms, especially for, let's say we add the, they got too close. Let's add the x. Let's say any position. You take the middle number. In this case, it's x. For the mean, the more what everyone usually calls an average, you just add everything,
So it's the
and then actually it will be better. It will
sum of the
actually be better
oddets.
called the arithmetic mean, not just any mean.
Yes. Okay. So it is the
Sum of addends over the number of addends.
over the number of others.
So in
Yes.
this case, the mean would become 28 plus x over 5. So this will require some casework because we do not know actually where what especially for the median, we do not know where what the value of x is equal to exactly. So we need to do a lot of cases. So the first case won't fit here. Case one. Well, x is
On top of the one. So if
case
you know
one.
it's
Case one. When you put case, it would be better to use Roman numerals rather than normal numerals as the adopted standard. So for case one, let's say x is greater than 6 but is still less than 16. Then the median would be 6 because it's the middle number. So we want the mean and median to be equal. So the mean, which is 28 plus x over 5, oops, it selected somehow, over 5, should equal to be, should be equal to 6. But when we solve this, we see that 28 plus x equals 30. So then x will be equal to 2. But we just said that x must be greater than 6 but less than 16. So this is impossible. So when we do the next case, for the next case, what if in we move the x a little to the right when x is either 16 or 6. 16 or greater. So here actually in the first case, I forgot to point out, if in case x was 6, then it would the ascending order would be the same and 6 would still be chosen. And even if x itself is 16, 6 will still be chosen because the one in the middle. So now x is greater than or equal to 16. When it is, then the median will still be 6, and then we see the same argument will occur. The median will still be 6, so the mean should be also be 6, and then we end up with the same impossible case that x is equal to 2 when we assume that it is greater than or equal to 16. So, when we go backwards this time from 6, so what if it is in between 4 and 2? Can either be, actually it kind of matters whether it will be 2, 4 or 6. So and X is, actually I don't think there will be any issues if it will be either X or 4. Anyway, so the median this time will be 4, so the mean uh, should equal 4. And then we end up with a worse situation than before where x is equal to -8, which is obviously impossible because we just assume that it's greater than 2 or 4. I did not use the highlight. That's hinge.
Okay, third case is not possible also.
So we move on to the pretty much the last case because we did this stuff. I will be making a sort of a summary of the cases we have done so far. Where 2, 4, 6, 16, we did when x was here, either 6 or 16. Alright, yes. When x is 16 and above. We also tried when x is between uh
How about if X
when
is your,
uh if x is the when if when
if X is your median?
if x is your median, so in this case for 2 for x 16, looks like 616, no, first median of course is x. This is when it's between 4 and 6 inclusive. Will it matter? No. Okay. So 28 plus x over 5 equals x itself. So equals 5x, 28 plus x. So 28 equals 4x, x equals 7. But look what happens. We assume that it's in between 6 and 4, but in fact it is not. So this again is an impossible case.
Yes.
Somehow it failed. So I will be putting that new think we discovered. Okay, so we have only one choice. One choice left.
When
What happens when x is wait, I should forgot to put the case. Case B finally. It's the final case. So what happens when x is behind or equal to 2 completely? So this time 4 will be the median. Then x will be equal to -8. So actually, when x is equal to when x is equal to 2, we can just suddenly say that x is completely behind or equal to 2. But now we group it into a sort of subset subkeys. When x is equal to 2, of course this is a violation. So this first subcase is not true. X cannot be equal to 2. But when we go to the next B, I will put already our discoveries. What happens when x is strictly less than 2? Then when x is strictly less than 2, this is not a violation because -8 is obviously less than 2. So -8 is in fact a root. So x equals -8 for this subcase. So I think we explored all cases.
yes.
I will just put what we discovered. So it is legal for us to do anything behind 2 completely. So this is actually the only value of x where the mean and median for these numbers
Five
are
numbers are
equal.
equal, yes.
So I guess this wraps up our video. So thanks for watching.
Hope you learned
A lot from this
from
video.
these two problems.
So,
Bye bye.
bye.